Hi, good morning, everyone. Today we will be discussing about linking pore solution chemistry of concrete to ASR potential as a machine learning approach. Uh, my name is Pravin, and I'm a graduate research assistant at Texas A&M Transportation Institute, Texas A&M University. Uh, the principal investigator for our current project, as well as the research mentor, is Dr. Anul Mukhopadhyay. He's a research scientist at Materials and Pavements Group at TTI. And we also have Dr. Kaiwai Lu Victor, who is an assistant research scientist and lab manager at TTI. So this is a presentation outline that we are going to be discussing today. First, we would be talking about what are the different approaches to evaluate the ASR potential with the current test methods as well as the novel performance-based approach methods. Second, we would be looking at what is the significance of the pore solution chemistry on the ASR potential. How does it vary according to the different SCMs and for the different concrete mixes, and how it should be considered for the performance evaluation. And finally, we would be talking about a performance-based ASR evaluation towards a mixture qualification, and finally ending with the conclusions. So first, discussing the traditional approaches to evaluate ASR potential, we have ASTM C 1260, the mortar bar, and also the ASTM C 1293. First one is actually accelerated, which is probably around 14 days, and tested under severe test conditions. But sometimes the results have been found to be not correlated to the field performance, whereas the 1293, the minimum duration for the test period is minimum 1 year. Let's look at what is actually a limitation of these approaches. That these ASR tests really do not address the aggregate reactivity prior to the loosened concrete structures, and determine the threshold alkalinity of the aggregates is actually the primary step. Also, the effect of alkalis from cement and the SCMs on the ASR at the direct level of pore solution alkalinity is not considered. These tests are usually performed at boosted levels of alkali, so the testing is not really performed at the level of the real pore solution alkalinity. And also, they do not really address the long-term performance of fly ash, specifically fly ash in concrete structures. So the new approach, which is the accelerated concrete cylinder test approach, actually presents a more performance-based evaluation to evaluate ASR potential, and also design the optimum replacement percentage for different SCMs. Yes, so there are the 4 different steps to this entire evaluation. The first is determining aggregate reactivity, and we could be using any method as in the CAP based, which is cumulative aggregate potential based reactivity, or VCMD test, which usually takes around 5 days, or the ACCT test, which takes about 28 to 45 days. The essence here is to really determine what the aggregate reactivity is on the first step. Once we determine the aggregate reactivity, the next step would be actually heading towards deciding the optimum SCM replacement, which is a performance-based mixed design formulation. Now, for this, we really need to evaluate what the pore solution chemistry is for each concrete mix for different SCM replacement levels. And once we have the pore solution alkalinity determined, we would go to step 3. And at this stage, it's just a comparison assessment. Is the pore solution alkalinity of my mix is lower or higher than the threshold level alkalinity of the aggregate that would be used in structure? If it's lower, then it's not a problem. If it's equal, it would perform well, but only under mild conditions. If it's greater, then the mix design probably needs revision with a higher SCM dosage. Once an optimum level of SCM has been determined at this stage, we finally go to the mix design verification, where the ACCT test is performed for the desired optimum SCM replacement level. This is performed at no alkali boosting, so actual pore solution alkalinity to determine the true performance. And it is the third step, which would be the aspect of the further discussions. Let's look at like the overall objective of the alkali silica reaction and how SCMs play a crucial role in that regard. Now, definitely SCMs have been recognized as one of the most effective measures to prevent ASR. And of course, the fly ash has been widely used by different state DOTs for ASR control. But what has been really happening is that due to environmental regulations, there have been a lot of changes in the power plant operations. So this continuously changes the composition of the coal or indeed the fly ash composition that is coming out of this coal power plants. So this actually points to a very important fundamental question or the aspect that any new test method that to be applicable, it first has to address the performance, which has to be a function of the composition of the SCM. As the SCM, the nature of the SCM would be changing, the fly ash composition would be changing, the performance would be changing as well. So these test methods need to address the performance based on the composition. And on that scale, like the Pore solution is the first aspect that we would be looking at. Just a quick discussion on how SCMs actually influence the Pore solution chemistry. Now, whenever we look at the bulk XRF data, we look at Na2O or the K2O, the sodium oxide and potassium oxide. The value there is actually essentially comprised of two separate parameters. One is the crystalline phase or the readily soluble fraction, which is usually available within first 24 hours or first 24 to 72 hours of the hydration reaction starts. And the second component is the bound phase, which is gradually put into Pore solution as the clinker hydrates or as the pozzolanic reaction happens, they are released into the Pore solution. So when we look at some of the factors why SCMs actually contribute to a lower alkali Pore solution, one of the common aspects why it's commonly attributed to is the cement dilution effect. But you see, but you see the graphs on the right, this would not always be true. If you replace equal amount of cement with a similar equal amount of even class F fly ash, the one that we used in our project, it definitely has the higher alkalis as compared to the cement, and class C had significantly higher. So cement dilution effect for fly ashes have to be considered with a little bit more caution. And second is the slow release of bound alkalis. When we measured the alkali sulfates or the crystalline fractions that are readily available from these, the table on the right shows it's around average of 75% for cement, but for class F fly ash, it's around like 38 to 40%. So that means 60% of this, the total alkalis are actually released during the entire life of hydration. And if you see the degree of hydration that we measured at 90 days, for cement, it was approximately 80% cement was hydrated, but for the class C fly ash, it only hydrated 50%. And for class F, it was even lower, which was around 40%. So why is the composition really important, and why do we have to consider that for really deciding the behavior of these ashes? So this is the QXRD quantification of both class F and class C fly ash. As we actually saw on the previous slide, the contribution of the alkali directly comes from the crystalline phases, and for the class C, we see a significant higher level of alkalis or crystalline phases as compared to class F fly ash. Now, this is directly reflected in figure 3, where if you see on the x-axis the available alkali to total alkali ratio, for the class F, it's significantly lower, or it's actually lower than class C. What is important here to notice that we see two distinct peaks, as in there is a definite distinct level of alkali difference in alkali contribution from F and C ash just based on its composition. And fourth important aspect that we also need to consider with the SEMs is these SEMs add silica or the amorphous silica. So as the silica content increases, the C by S ratio in the overall hydrated phase or the CSH decreases. At the lower CSH or C to S ratio, it has the capacity to bind alkali and further lower the pore solution concentration. If you look at the figure 4, the lower the C by S ratio or the higher the silica content, the lower is the available alkali as a fraction of threshold alkali. And this phenomenon, also known as alkali binding, it decreases in the order of silica fume, class F fly ash, and then class C fly ash. So let's look at some of the techniques that are available currently to determine the pore solution concentration of concrete mixes, even with the SEMs. When we are referring to pore solution concentration, we are generally referring to sodium and the potassium concentration. The extraction technique is one of the most common approaches, but it's highly complex procedure, limited to very early ages. There are extremely few studies which have reported the extraction values up to the age of like 56 and 90 days. But then at the later ages, the dissolution of alkali in pore solution increases with the applied pressure. So at the higher age, more the pressure applied, so we get artificially high concentrations, which is also a factor to be considered. Towards the modeling, NIST model is one of the widely used approach, but one of the things that NIST model does is it actually assumes a default 75% alkali contribution from all its ingredient phases. If we remember, like, our fly ash cement and fly ash composition, the 75% was the average contribution from cement, which appeared to match with cement. But for the fly ashes, it represents an overestimation, and this is moreover so for class F fly ash. Now, another thing that NIST model does is it does incorporate alkali binding from silica fume, but it does not take into consideration the alkali binding effects of let's say class F fly ash, which also is a significant source of amorphous silica. So this is a novel technique that was developed in a previous research in 2019. This is the combined NIST plus ASTM C 311 approach. So from our previous discussion, what we have realized is whenever we are considering SCMs or fly ashes, we really have to look at what is the level of available alkali from these fly ashes, and which cannot be assumed as a fixed percentage or a constant value. And this approach actually allows to incorporate available alkalis based on composition. And when you combine this approach with the NIST model, the alkali bindings from the silica fume also come into play. So the results from the NIST and the NIST plus ASTM C 311 are actually presented in the graph there. The blue bars represent the NIST plus ASTM C 311 versus the NIST in the gray. There was also thermodynamic GEMS model that was developed for these composition of fly ashes and the replacement levels, and the values are shown with the lines and have been compared to the extraction values. So for the cement, of course, since there is no SCM, both the NIST and the NIST ASTM C 311, the combined approach, perform pretty well. But we really see a beautiful results when we look at class F fly ash incorporation, because earlier we saw class F fly ash contribution to available alkali significantly lower than the cement. Although the bulk alkali may be higher, but the available alkali is lower. So assuming a default percentage of 75 may not be an appropriate method, and we see a huge difference in prediction between the two approaches. Now, when you validate this with the extraction studies, the values for the combined NIST and ASTM C 311 approach match pretty well with the GEMS modeling, the thermodynamic model, and also from the extraction studies. The thing is, the thermodynamic model is highly reliable method, but it's also presents a very complicated technique for industry practitioners. So here, the important aspect is the NIST, the combined NIST and ASTM C311 approach. The focus is it presents a highly simplified approach and also a reliable technique for both research and industry practitioners. And it does account to estimate the PSC with the SEMs with a very high level of reliability. Now, the aspect of to determine the available alkalis from the fly ash, it's usually preferred as an experimental technique, but the test is usually criticized for its very long duration and high variability. The prediction models often rely on the R-square approach, or the least sum of squares. So we have different equations coming from different studies, but then when you problem is the equations perform very well to the local studies or the studied fly ashes, but they do not incorporate a global variability. And that's where the machine learning aspect really comes in handy. As we see from this figure on the left, this is essentially showing us that the available consideration to available alkali cannot be just from any one significant or any one or two parameters, or just on the bulk composition, bulk Na2O or bulk SiO2. Almost all the entire composition plays certain amount of role uh, to overall contribution of the available alkalis from the fly ash. And this is actually an important stage, an important point to consider. So in this machine learning model, like we compiled a database of the test results from almost covering last 30 years to train and test the model. And we incorporated the Monte Carlo Markov chain method. It's important to realize that to actually incorporate a global variability, we also need to incorporate the variability in the parameters estimated itself. It would not just not only be good to estimate a single value, but we would need to estimate it on the basis of the confidence interval. And that actually is very important, because in an extreme critical situations, you may have to test, or your consideration has to be towards the level at the 95% confidence, or the upper threshold level, or for a very moderate or low severe conditions, we could go at even 5%. So like this model, one of the test value that we provided, the actual test result was 1.5 and the model predicted 1.4. But this consideration of the overall confidence interval, the 5 and 95%, allows us to actually incorporate more reliability into overall estimation. So finally, we would look at like how these all actually come together. So our performance-based approach, of course, developed by the previous research from 2015 by Dr. Mukhopadhyay and Dr. Victor. The first step is to determine the aggregate reactivity, and as soon as the threshold alkalinity and TAL are established for the aggregate, this combined approach with the machine learning can be can be used to directly determine what is the whole solution alkalinity for different levels of fly ash. And this can be compared to the threshold alkalinity to take very quick decisions on what the optimum replacement percent for the various SCMs could be. And finally, it finally would go to the mixed validation study, which probably the ACCT based test, which probably takes around 75 to 90 days. And we see that once, as soon as the pore solution alkalinity by this method was deemed over the threshold alkalinity, the expansion from the ACCT was more than 0.04%. So in conclusion, we would like to say that the performance-based test approaches are really required to evaluate the ASR reactivity. The first consideration is towards the mixture design. The optimum replacement percentage should be based on the composition and the performance. Once the optimum level of replacement has been determined, the mixture acceptance testing could be performed by the ACCT test method, which usually takes around 75 to 90 days. And it could be performed at the level of pore solution, concentration, alkalinity, or low alkali loadings. Now, to estimate PSC from SEMs, the key component is to focus on the chemical composition. So our approach, the NIST and ASTM C311 approach, provides a very reliable and
wrap it up quickly, please. That would be great.
Yes. And finally, I think the overall efforts, research efforts, promote sustainable use of SEMs to make long-lasting, durable concrete. Just like to acknowledge sponsors: Texas Department of Transportation, American Coal Ash Association Foundation, United States Bureau of Reclamation, and Los Alamos National Lab.